Hi guys, this is MD Basid, and we are doing project problem 5. My group member is Tamina Mia, myself, Kaniz Rahman, and Shahul Hamid. And our question asks, suppose the circles of equal diameter are packed tightly in n rows inside an equilateral triangle. See the picture below. Our picture is in the next page, where the case n equal 4 is shown. So it said let P of n be the picture showing the n rows of circles, and let A of n be the total area occupied by the n rows of circles. Okay, and part A asks us to show picture 1, picture 2, and picture 3, and then compute area 1, area 2, and area 3. And part B asks us to compute area 4, and part C asks us to get a general formula for A of n, area of n rows, and part D asks us to get the limit as n goes to infinity of the area A of n. And part E says explain the significance of the result in part D. For instance, how much of the area of the triangle will the will the rows of circle eventually occupy to the nearest percent as n goes to positive infinity. And this is the picture they were talking about. And I'll pass it over to Tamina.
Okay, so um, part A asks show P1, P2, P3, and then compute A1, A2, A3. So we're going to start off with showing P1, P2, P3. So for this problem, we are told that we're dealing with circles of equal diameter that are packed tightly in n rows inside an equilateral triangle. In the introduction, if I go back, it said to let Pn be the picture showing the n rows of circles, right? So when they ask for P1, P2, P3, they're basing it off of P of n. So if we use that logic, we can conclude that P1 right here is an equilateral triangle that has one row because of the one right here, which consists of just one circle. So P2 also is an equilateral triangle that has two rows because of the two right here, and it consists of three circles. And lastly, P3, the three here, which means three rows um, of circles, and it consists of six circles right here. So that's pretty simple. So now let's get to computing A1, A2, and A3. But before we compute, I want to introduce what A of n is and how we can start computing it. So in this problem, it tells us that, let's go back, to let A of n be the total area occupied by n rows of circles. So in order to do this, or to start, let's talk about some basics. So we know that the area of a circle is pi r squared. But if we go back to the picture they gave us, they have the length of the side of the triangle, which is L. So now since we have length, we have to factor in the length that they gave us. So therefore, we have to find a substitute for r because this problem is in terms of L. So to find another relationship between the circle and the triangle, if we go to A of 1 right here, so I can show you an example of what I'm talking about, we found our relationship to be that if we create a a dot right here in the center of the circle and drag it to the corner of the triangle, and then start back here from the center and then drag it down, we create a right triangle. And we can see that this right triangle connects the circle and the triangle together. So now let's focus on just the right triangle that we created. So here, this line right here is our radius, and this whole line right here would be L, right? Which they told us in the problem, but we're only focused on this right triangle that we created, so it would make sense to make this L over 2, because this is half of L. So now we have, the radius right here, and we have the L over 2 right here. So now since we know this is a 90, 30, 60 triangle, and we have R on this side and L over 2 on this side, we have to find a trig function that includes the R and the L over 2. So we found that if we use tan of 30, tan is opposite over adjacent. So if you can see, if we use tan of 30, opposite would be R and adjacent would be L over 2. So that's why over here we have tan 30 opposite over adjacent. Right. So now, since we have some background of A of n, now we can start to compute. So, so here's A of 1. So we have our right triangle right here, created, and we have our 30 degrees labeled right here, our L over 2, and our R. You know, if you can see, this is a radius. So over here, if you look to the right, we have tan 30 opposite over adjacent, what I was talking about. We simplify tan 30, which is 1 over square root of 3, and the opposite is r, and adjacent is L over 2. Now, we know that our area is going to be pi r squared, right? So, and we have L, so I was saying we need r in terms of L, right? So we can plug it into the area function of a circle. So if we cross multiply, and we simplify a little bit, we have r equals L over 2 square root of 3. And now r is in terms of L, and we just plug it into our area function pi r, this is our r, and then squared. And right here, since there's nothing in front of the pi, you'll see later on that in the next problem there's a number in front of it. All it means is that there's one circle. So there should be a 1 in front of the pi, but that's just pi, right? We'll learn about that more later on when we look at the trends, but that's just what it is for. So let's start with A of 2. A of 2 is similar, but a little different. So now we have, if you can see, we have two circles in the bottom row that we have to account for now. So we're going to start off how we did in the first computing A of 1. We have a right triangle created right here from the center of the circle, dragged down to the corner of the triangle, and then the center of the circle dragged down to make a right triangle. But if you can see, we have another circle over here, so we also made a right triangle connecting this center of circle to this side of the corner of the right triangle, and then straight down. So we have two right triangles here. And then you can see we have this little area, this little section right here. So we made this into a rectangle. So now we have our new length right here. This is still L. This whole bottom, we didn't change anything. This is still L. But we now have another right triangle, right? So instead of making it L over 2, we're going to make it Z, so we don't get mixed up, right? And plus, it's not L over 2 anymore because it's not half. We don't know what it is. So we're going to just make it Z, and we're going to call this Z. So now if you look closely to figure out what the length of this is, you can see that there's a radius here of the circle. There's half a radius right, there's a radius right here, and there's a radius right here. That would be 2r. So our whole length would be 2z, this z and this z right here, the length of this right triangle and the length of this right triangle. And then we have our 2r, which is the one radius right here of this circle and another radius right here of this circle because we're accounting for two circles. So our new length would be L equals 2z plus 2r. So now we're going to do the same thing, tan of 30, right? So tan of 30, we still have our r right here, and now it's our z. So this is our opposite, and this is our adjacent. Same thing here, we can use tan 30 because look, this is our 30 degrees, this is our r, and this is our z. So over here, if you look, tan 30, opposite, which is our r, and adjacent, which is our z. So tan 30, we simplified right here, 1 over square root of 3 equals r over z. We solve for z, and we're going to solve for z to plug it into our length formula that we created. So we can get it in terms of r, and then make it in terms of, get it in terms of L, and then get it in terms of r to plug into our area function. So we put in our z to our formula right here. So L equals 2 square root of 3r plus 2r. Took out an r, divided this whole thing towards L, and then we have r equals L over 2 square root of 3 plus 2. And we plugged it into our pi r squared function. And here what I was talking about, the 3 in front of the pi, is just the 3 circles inside the triangle. So now computing A of 3. Same thing of A of 2. However, we added another circle, right? So it's another circle we have to account for. So similarly, we have our two triangles here, right? And in the corners. And as you can see, there is a little trend. The right triangles in the corner stay the same. It's always going to be two right triangles starting from A of 2. But the more circles you add, the longer this length right here will be, the radius right here. So we have our Z here, and now we have 3 circles you have to count for. So we have this long rectangle, it's double, or we'll see later on, but it looks like it's double of what it was last time, the length right here. So we have 1 radius, 2, 3, 4. So that's how we got our 4R. So we have Z, 4R, Z, and it's still our new length. So we're going to do L equals 2Z, which is 1 here, plus 4R, which is this 4 radius I was just talking about. And same thing, our tan 30 is R over Z, because our 30 is here, our 30 is here, and then R opposite, Z still our adjacent, so that didn't change. So we simplified it here, R over Z, and then did the same thing, and we just plugged it into our new formula for length, and we did the same steps. We just got it in terms of R, and then plugged it in, got it in terms of L, plugged it in, and then plugged it into our area function. And the 6 here is, like I said before, the number of circles. If you can see, there's 6 circles here, and that's why there's 6's in the front of the pie. So now for part B, it's asking to compute A of 4. So in order to do A of 4, we need to know what P of 4 is, which it didn't ask us to show in part A, but since we already knew how to find P1, P2, P3, it's simple. It's same thing for P4. It's 4 rows of circles, and there's how many circles here? 10. So same thing to compute A of 4. Here's our picture of P4. Like I said, the two right triangles are always going to stay the same here. And then we have our Z and our Z, and then now another circle we have to account for right here. And so our rectangle just got even longer. So now we have 1, 2, 3, 4, 5, 6. If you followed along with the mouse, you can see there's 6 radiuses to account for now. So that's going to be our new length. So our length is L equals 2Z plus 6R. So now the same thing applies, tan 30 over R over Z. That hasn't changed because the right triangles, we haven't touched them since A of 2. So yeah, so you find equal to Z, and then plug it into our Z for our length formula to get in terms of R, and then you're going to get in terms of L, and then you're going to plug it into your pi r squared formula to get A of 4, and then the 10 here, like I said before, is just the number of circles inside the triangle. So now I'm going to pass it on to MD.
So yeah, so part C asks us to find the general formula for A of n, and A of n is the same as f of n. It's just a function. So we use tcons to find the general formula. So far, Tamina showed us this, that A of 1 is this formula, A of 2 is this formula, A of 3 is this formula, A of 4 is this formula. So, okay. So now, let us see the similarities of each function. We have pi in each function. So let me go back. I'll show you pi. So you see, we have pi in this, pi, pi, pi. Okay. And we also have L divided by 2 square root of 3, and that's to the power of 2. And we have, let me show you that. See, we have this right here to the squared, right here to the square power, right here to the power of 2. So now let's see the difference of each function. Number fun of the pi are 1, 3, 6, and 10. So they are changing. See, there's 1, there's 3, there's 6, and 10. And also it says inside the power, the denominator, we have plus 2, plus 4, plus 6. So here's there's nothing, but here plus 2, here's plus 4, and here's plus 6. Okay. So for the number of circles, we use quadratic sequence, and quadratic sequence is is the second difference. So let me show you an example. So here's an example. So as imagine this is our circles like 1, 4, 9, 16, 25, 36. The difference here is plus 3, plus 5, plus 6, but there is no common difference. But after we take the second difference, that's called the quadratic difference. So we have plus 2, plus 2, plus 2, plus 2, and that's the common difference. So let's keep this in mind, and we'll use this for our circles. So A of n, A of n, A of one has one circles, A of two have three circles, A of three have six circles, and A of four have 10 circles, right? So the first difference is two, between this is two, between this two is three, between this two is four, right? So the second difference is 1, 1. See, that's the common difference. Is the second difference that the quadratic, so we would do a quadratic sequence. And this is the formula for the quadratic sequence, which is a n squared plus b of n plus c. In this case, remember the formula like x, n is same thing as x. So, okay. So in this thing, I didn't show you guys, but quadratic sequence, it just says like whatever this is, we just divide it by two to get the first term a. So I just divided by, which is one divided by two is one half, right? So yeah, and then we get b and c. So how do we get b? We do the same thing for b. So circles we have 1, 3, 6, and 10, right? And we just use the first a n squared to get to see the difference, to see the change. So I plugged in for one circle. I plugged into the formula. We already know a is one half. Just plug this in. We got one half. For this we got one. For this we got one of five. Then plus this we got two. But right away we get a common difference. So this is not a quadratic. This is just in this case this is n. We say x in other equation, but this is just n in this case. So and and we have b right now. So one half is b. One half, one half, one half. So this is the first change, and right away we get a difference, and that's the common difference. Right away we get it. So that's not a quadratic sequence. This is just the b we got. Now the C in this sequence, quadratic sequence, it just says C is just first term, uh, first term that is changing. But in this case, the first term is zero. With zero, one half, one, 1.5, 2, right? So zero is C. So now we get our general formula: one half n squared, one half n squared plus one half n. So we get b and a, right? So I simplify it to n squared plus n divided by 2, and then this is more simplified. And I'll pass it over. Oh, my bad. And I will show you the change in the denominator. So in the denominator, we use arithmetic sequence. So to find to do arithmetic sequence, we find the nth term, right? So a of n equal a1 plus n minus 1 to the d, and d is the common difference, right? So n term of the sequence a of 1, okay, n term of the sequence a of 1 is the first term of the sequence, and d is the common difference, right? So as you can see, we have a1, a2, a3, a4. And in the denominator, we have 0, 2, 4, and 6, right? And the common difference is 2, 2, 2. And the common difference is D in this case. So this is D, 2, 2, 2. So arithmetic equation is just a simple formula you use when there is like right away there is a common difference, and this is the d, and this is the formula given. So a of 1 is, as I said before, a of 1 is the first term. A of n, we are just finding the, this is the general form, and d is the common difference. So a of n, a of 1, a of n is the general formula. A of 1 is the first term, which is 0, and this is given in the formula, so we leave it alone. And d is the common difference, so it's 2, so right here, and we simplified it to get 2n minus 2, right? Then this is the general formula we get. And then do we know if it works? Let's check it out. So I plugged in if n equals 1. After I plugged in 1 of nth row, we get this. And as Tamina showed before, we get the same thing right here. So I said maybe the first one works. It's just 1. Let's just try another number. So we tried 4. So after I plugged in 4, we get 10 pi over 10 pi, which is the 10 circles pi, and we got this, which Tamina showed before, where we have four rows. So it works and I'll pass it over to um, Kaniz.
Hey guys, I'm Shahul, and for part D, we are asked to take the limit of the general formula A of n, and this right here is the general formula for A of n. Now let's simplify that part 2 over here by squaring the value inside the second part. When you square the value inside the second part, you get this. And let's simplify further by factoring out 4 in the denominator. When you factor out 4 in the denominator, you get this. And the value inside the parentheses is a simplified version of the value in the previous. And now let's take the limit as n goes to infinity. When we take the limit as n goes to infinity, we don't care about the n's because it goes to infinity. So then we care about the numbers which is left over here. The numbers which is left over is 1/2 pi n l squared over 4, and pi over 8 l squared is the simplified version of the 1/2 pi n l squared over 4. Now I'm going to pass it to Kaniz.
Hi guys, so I am doing part E, and part E is asking us to find the significance of part D. So as Shahul did part D, you guys in, I'm going to talk about the significance of part D. So the importance of part D is that it gives us the limit area, and when we divide it by the actual, we realize that there is still space left. And as my teammate have mentioned, that before that a circle has a fixed shape, and in this case, the circle cannot overlap. So we have still space left. Part D has also give us the final, or let us see the future. What if we wanted the radius to be infinitely small? We see that we'll get that answer of pi over 8 l squared. This is the limit, not the actual. So if you want a certain number, just plug it in and you'll get an actual value. Also for part E, it asks us to find the nearest percent. So to do that, we're just gonna take whatever we have found for limit of a sub n as n goes to infinity and divide it by the total area of the equilateral triangle, which is root 3 over 4 l squared. And if we do that math, we end up with 91%, which is the percent they're asking for. And now I'll pass it over to MD to wrap it up, our presentation.
So, in conclusion, some of the technique we use in this problem were geometric sequence and limits and trig to solve. We use the formula for the area of a circle to compute the area as well as finding the limit. And limit is the value that a function or sequence approaches as the input or index approaches some value. Limits are essential to calculus, and we use them to define continuity, derivatives, and integrals. It was fascinating to see that after filling out the whole triangle with infinite amount of circles, that there were still space left. Thank you guys, and have a good one.